then in the second term here, we have a product over these three factors. 1, 2, I don't have any more. Times, this is now an ordinary multiplication. Okay, so these three pieces here come from these three line segments. Okay, so that's just a pictographic way to represent a term in the coproduct. The magical thing that Goncharov showed is that this coproduct is compatible with multiplication, and hence these i's are elements of what we call a top algebra. In case this is a little bit too abstract, let me write an explicit formula for the coproduct of the ordinary polylogarithm function dk. Example, delta dk of z is equal to the function 1 tensor dk of z plus the sum n equals 1 to k minus 1 d n minus k, k minus n, z tensor log to the power k z over, I just wanted to put a 1 over k factorial, but I ended up deleting my formula. That should be n over n factorial. Okay. Another important thing about this coproduct, which is evident from that formula, but I didn't mention it yet, is that it's weight preserving if you take the sum of the weights of the individual constituents here. So here, the coproduct takes a function of weight k and breaks it up into a sum of terms, but in each term, the total weight is preserved. That has weight 0, that has weight k, that has weight k minus n, that has weight n, so they add up to weight k, as does that term as well. Or another way to say it is that the space of these iterated integrals is naturally graded by the weight, and the coproduct respects this grading. There's an additional structure that we can define that's important for analyzing some of the deeper mathematical content of these functions. So if we let A be the algebra, or I should say co-algebra, of all such functions graded by weight, and I let L be the quotient here, A plus means strictly positive weight, greater than 0. What I'm doing here is I'm forming the quotient space where, in this quotient space, you identify two functions of that type if they differ by something that can be written as a linear combination of products of lower weight functions, i.e., in L, v2 of x plus log squared of x is identified with v2 of x. Because this term, while it has weight 2, it's a perfectly fine element of the algebra A, it drops out in this quotient space, so these two things are considered to be equivalent functions in the quotient space. This is interesting to mathematicians for the following reason, that the restriction of the coproduct to the quotient space, which we call L, I'm sorry, delta, I'm light on sleep, I apologize. Satisfies remarkable identity. You can check it's true. You can check it's true just by the definition. So if you apply the coproduct capital delta twice, you can check that inevitably you get something that can be represented as a linear combination of products of lower things, and hence it's zero inside this quotient space. Okay, so mathematicians and physicists alike love operators that square to zero because we can do all sorts of fun cohomological analyses with them. But in the case of a coalgebra, this is a particularly interesting structure. Delta is the co-bracket of a co-Lie algebra. I'm not going to say any more about that, but if you want more details, you can check Wikipedia. There's an excellent entry in Wikipedia on the concept of Lie coalgebra. I think it's more conventionally called Lie coalgebra. And the point is that the co-bracket operator squaring to zero is the co-statement to the Jacobi identity of the Lie algebra. So it's really easy to prove by a few simple steps that delta squared equals zero implies the Lie algebra, implies the Jacobi identity in the Lie coalgebra, and vice versa. The Jacobi identity implies delta squared equals zero. Okay.
What kinds of Lie algebras do you typically get?
Well,
I mean, compact or non-compact?
Here, of course, we have an infinite dimensional Lie coalgebra.
Yeah.
But I think in principle, I don't know, but I imagine they consider it a huge variety. Okay. So one more comment. Notice that this coproduct splits into, it's a sum of different terms, and they live in different spaces. Okay, so this is a formal sum of objects that live in different spaces, and sometimes it's useful to isolate a particular term. So we might call this term, for example, the 0, k component of the coproduct. This term here is the k minus n, n component of the coproduct. And this here, of course, is the k, 0 element of the coproduct. And similarly, the co-bracket delta respects the weight. So delta maps L into L wedge L. There's no component proportional to the, if you have a tensor product of two spaces, you can decompose it into the symmetric part and the anti-symmetric part. But in the quotient space here, the symmetric part is zero. Because if you have anytime you have a function that has anytime you take a coproduct of a product of two functions, it's symmetric, and vice versa. Anything symmetric necessarily comes from the coproduct of a product of two functions, so it's zero in the quotient space. So delta always maps into only the anti-symmetric component here. You never get a piece in the symmetric component. So for example, and I might use this later, if we look at two-loop amplitudes, where we're interested in weight 4, delta maps L4 into only two components, L2 wedge L2, L3 wedge L1. You don't have a piece like this because 1 is a trivial element in the quotient space. Okay. Are there any questions about this? Because now I'm going to turn my attention to applying some of this technology to some actual scattering amplitudes and superambulance. Except that. Except there's one more crucial ingredient. Very, very crucial. We can, of course, iterate the coproduct. So, for example, in one of these terms, well, in any of these terms, you can hit delta again and keep breaking up these pieces into individual constituents. Okay? So think about delta as a hammer that splits your function into half, into pieces, into 2 pieces, and you can keep hitting with your hammer until you break up your function into atoms. So the symbol of the polygon function is defined as the kth iterated coproduct, where you've broken everything up into functions of weight 1. So if you take a function of weight k and you take its iterated coproduct, which I'll denote by delta to the k power schematically, this is going to be a linear combination of things like log A1 tensor log AK. So at weight 1, the only function you have is the logarithm function. So if you've completely smashed your function using the coproduct, you're just going to get a linear combination of logs. And often we use the schematic shorthand. We abbreviate this by simply omitting the log. So we would say that the symbol of this FK is the same linear combination of formal objects of this form. So, fortunately, I still have some nice formulas on the board from my example. So let's revisit them in light of our fancy new coproduct technology. The symbol, well, another way to compute the symbol, and this is maybe easier in practice, is the following. If you have a function of weight k, then it has the property, and this also ties in with the first part of my talk, a function of weight k has the property that it can be written as a linear combination of functions of weight k minus 1, d log certain rational functions Ri. Now you can iterate this, right? You can calculate the differential of these individual weight k minus 1 functions, and if each of those is an honest weight k minus 1 function, then it should be expressible as a linear combination of functions of weight k minus 2, etc. Until finally, at the end of this procedure, you'll have a collection of numbers. So you'll come down to coefficient functions that have k superscripts here, but their weight 0, so they'll just be numbers. And then the symbol of that function is defined as the linear combination. You sum over all these variables, you put these numbers. Okay. Now the symbol has some important properties. Note that, for example, it has a multiplicative property. Because even though we use a notational shorthand where we omit writing this logarithm explicitly, of course we have to remember that secretly all of this comes from taking d logs. And since d log of b times c is equal to d log b plus d log c, we have that identity. And also constants drop out. If you have a number like 1, okay, what's d log of 1? It's 0. So in particular, this implies, for example, that if you have an inverse of something, that's equal to minus the symbol within the numerator. Okay. So now we can use these definitions to compute some simple examples of symbols. The weight2 function log x times log y is given by that. The symbol of Lie2 of x is minus 1 minus x tensor x. And the symbol of our friend here is still on the board. Oh, sorry, it's a different friend. It's the one loop massive box. X plus tensor 1 minus x plus minus 1 minus x plus tensor x plus. So the idea behind the symbol, you should really think of the symbol kind of as a very particular representation of the integrand. It's a representation of the integrand because if you go back to what I said where I defined these iterated integrals over a line just in terms of the rational function. So remember that formula I gave in terms of the iterated integral of rational functions. Those end up being exactly the symbol entries. So I deleted it now, but I'll remind you in this formula. This has symbol of tk being R1 tensor up to Rk. So this is really just a representation of a particular representation of the integrand. And notice that in particular, you can use this relation to, if someone hands you a symbol, in principle, you can just define a function using that symbol by writing down an iterated integral of this form. Now, if you want to take that symbol and write it in terms of other previously known functions like polylogs or Goncharov polylogs, then some work, of course, might be required. But in principle, given any symbol of this form, you can immediately define it as an iterated integral of that type, assuming it's integrable, of course.
There's some loss of information, though, right?
Yeah, right. So the loss, it's important to describe the loss of information. In fact, I have an example of that. The loss of information has to do with the fact, well, the way to think about the loss of information here is that the symbol has no information about what branch, path you've chosen to integrate on. So if you switch from one path to another, and in the process of doing that, you cross a pole in one of your rational functions, then the new function you're going to get is going to differ from your old function by 2 pi I times the residue at that pole, which is necessarily going to be a function of weight 1 degree less. So the symbol loses information about functions of lower transcendentality. So let me show you a cute little exercise of something you can do with the symbol. One of the big utilities of the symbol is that you can use it to trivialize polylogarithm identities, which can easily get complicated if you go to higher weight. Consider the function d2 of 1 minus x. Okay, the symbol of this, using the result from over there on the board, is minus x tensor 1 minus x. But if I want to, I can add 0 in the form of, I'll just write it like this, minus 1 minus x tensor x plus 1 minus x tensor x minus x tensor 1 minus x. Oops, and I have a sign. Let's see. Yeah. Okay, these two terms add up to 0, so all I did was add 0 to that expression. But now notice that this thing is the symbol of minus d2 of x. And this thing over here is the symbol of minus log x times log 1 minus x. Oh, well, strictly speaking, I shouldn't say equal. I should say that's equal to the symbol of this quantity. So what I verified very quickly here is that the symbol of this Lie2 function is the same as the symbol of that Lie2 function. And so that implies that there should be an identity between these two, modulo possibly terms of lower transcendental weight. So you might be familiar with this as one of the D2 identities. So D2 of 1 minus x is equal to that. Minus log x log 1 minus x modulo pi. All right, since I only have 5 minutes left, let me see what's the most crucial thing. Right. So a lot of recent interest has been in two directions. First of all, using some of this mathematical technology to diagnose the structure of scattering amplitudes in n=4 supersymmetric Yang-Mills theory, and then, wherever possible, to use the structure to carry out new computations, hopefully with as minimal effort as possible. So let me provide you two aspects of this, and this will be really brief since I only have 5 minutes. So let me call this experimentation with n=4 loop amplitudes. Okay, so in 2011, Simon Caron-Boit performed an explicit computation, the differential of the two-loop n-particle MHD amplitude, specifically what we call the remainder function, which is what you get after a suitable subtraction of the infrared singularities using the BDS ansatz. But for all intents and purposes, just think about it as the two-loop n-particle MHD amplitude. And it's a rather long expression. He has a Mathematica file that spits out the answer for any given n. And you can start playing with it and see really interesting things. So for example, well, first of all, this is a two-loop amplitude, so it should have weight 4. So its differential should be a linear combination of terms with weight 3. So you run Simon's Mathematica code, and it spits out a bunch of terms. And one of them is something like this. Of course, it's going to involve the SL4C invariant scalar products, because it has to by dual conformal symmetry. And it has to involve quantities of the correct equal projective weight in the numerator and denominator. And you really get quite intricate things. So this is just an example of a term you get. And remember earlier in the lecture I mentioned that there can be a rather non-trivial algebraic relation between the arguments of your polylog functions and what you thought were the natural kinematic variables. In the case of the 4-mass box, we had to switch to these x plus and minus variables, which were related to the cross ratios u and v by this complicated square root. This is an even worse example. You could, if you wanted to, re-express this in terms of the natural Mandelstam variables appropriate for an 8-particle scattering amplitude, but it would be quite a mess. I mean, it's already a mess in momentum twistor space, but it would be even worse in terms of Mandelstam invariance. It would be a ratio of two things, both involving square roots. Okay, but one of the things that, if you like to dig into this kind of thing, his program will spit out things like this, but it will never. Okay, you could imagine that dual conformal invariance would allow, hypothetically, a term to appear where you have 1, 2, 3, 8 there and 1, 2, 5, 7 there. Okay, it still has 0 weight. But the switched term never appears. And so you might ask the question, why? And one of the things that we've discovered, primarily in collaboration with Sasha Goncharov and my former student John Golden and Anastasia Bolovic, Christian Vergu, and Miguel Palos has been involved, is we have at least a phenomenological explanation for some of the structure that we see in NHV amplitudes. We'd like to be able to make a more general statement, but there's very little data available in the literature. This is an experimental science where we look at results of complicated calculations and try to analyze them. It has been observed that the cross ratios which appear are not random, right? If you switched an 8 and a 7 there, you would get a cross ratio that I would consider random. They're not random. They are what we call cluster coordinates on this configuration space. Okay, I could say a lot more about that, but I won't. So the other aspect of this research program, which is under very active investigation, is suppose you take it as an ansatz that at least some class of amplitudes in superannular theory have this nice structure, that they should be polylogarithm functions, and that you understand, or you have some guess for what you think you understand should be the symbol alphabet, namely the collection of functions that can appear here. So that leads to what we call the bootstrap program. This has been heavily promoted to great success by Lance and his collaborators, and we've also dabbled in it. I'll mention a little bit. Make a guess that some amplitude is a polylog function, a generalized polylog function, with a certain symbol alphabet. And then try to determine it exactly, if you can, using physical constraints. These can be simple constraints like